Hello, welcome back. Here we are with our square root and our cubed root graphs. So remember, we've already done our squared graphs. That was our quadratics. Those were parabolas. And we've already done our cubic function graphs. That was x to the third power. So now we're taking the root of those. So how do we graph that square root and cube root function? Well, as always, we start with a table. And so let's think about what these functions are going to look like. This is going to look like the square root of some number, and then this is going to look like the cubed root of some number. So to make our life easy, we want to pick numbers to put into our table that are either perfect squares or perfect cubes. That way we can take the square root or the cubed root of them. So we're not worried about graphing these decimal numbers, right? So for square root, remember, we cannot take the even root of a negative number. So none of our x values are going to contain a negative. But 0 is technically a perfect square because 0 times 0 is 0. So I can take the square root of 0, and I do get 0. So that's going to be a point on my graph, 0, 0. I also know that 1 is a perfect square, and the square root of 1 is 1. 4 is a perfect square. The square root of 4 is 2. 9 is a perfect square. The square root of 9 is 3. So it's the opposite. It's the x's and the y's have flopped from the quadratic parent function to the square root parent function. And so now we know we can just graph these points. 0, 0, 1, 1, 4, 2, and 9, 3. And there is our graph. This square root function is never going to have these negative x values unless a transformation has been applied, like some kind of flip or something. Okay, so this is what the parent function looks like. Let's go ahead and work some cubic root functions out. Remember, we can take the odd root of a negative number because I know that a negative 2 to the third power is a negative 8. So I'm going to choose some negative and some positive perfect cubes. So I'm going to go with my negative 8, negative 2, negative 8, negative 1, 0, 1, and 8. Because I know the cubic root of negative 8 is negative 2, and the cubic root of negative 1 is negative 1, cubic root of 0 is 0, cubic root of 1 is 1, and the cubic root of 8 is 2. And so now I plot these points. I can start at 0, 0. I can plot negative 1, and a positive 1, positive 1. And then I can plot a negative 8, negative 2, and a positive 8, positive 2. And when I connect those points together, you're going to see that it looks very, very similar to our normal cubic parent function, just inversed, right? It is the inverse. Our x's and our y's have flipped, so that is the inverse. So it's kind of off to that side. It's sideways. We can still find the characteristics of both of these. Domain for the square root parent function. This is the first parent function that is not going to have the domain of negative infinity to positive infinity. For this domain, we are including 0, and we're only going to positive infinity. Same thing for our range. We're starting at 0, and we include it, and we go to positive infinity. This graph is increasing the entire time, so starting at 0 and going to infinity. It's decreasing nowhere. It's also positive the whole time, negative nowhere. There are no extrema. Remember, those are our maxes and mins. It's because there's no turning points. It doesn't go from increasing to decreasing or vice versa, meaning there are no extrema. There is also no symmetry. And the in behavior here is just going to be as x approaches positive infinity, y approaches positive infinity. We don't include the other because our x's don't approach negative infinity ever. We don't want to use a negative x value for that square root parent function. Domain for the cubic parent function, though, is still negative infinity to positive infinity. Even though it doesn't look it, the range is also negative infinity to positive infinity. It is increasing the entire time, meaning it's decreasing nowhere. It's positive from 0 to infinity, negative from negative infinity to 0. There's no extrema because, again, there's no turning points. Remember, symmetry, this has that origin symmetry, same as the cubic parent function. So if we reflect over the x and the y-axis, we get the same exact thing back. And then in behavior, as x approaches positive infinity, y approaches positive infinity. As x approaches negative, y also approaches negative. Very standard. Okay, transformations, the same ones we've been seeing all year long. If I'm subtracting something inside the parentheses, that means we're shifting right. If I'm adding something inside the parentheses, we're going left. If I'm multiplying inside those parentheses a number less than or less than 1 but bigger than 0, horizontal stretch. Bigger than 1, horizontal compression. A negative inside that parenthesis is going to be a reflection over the y-axis. And then on the outside of the parentheses, adding is going up, subtracting is going down. Multiplying outside of the parentheses, a number less than 1, bigger than 0, vertical compression. Bigger than 1, vertical stretch. And then, of course, a negative on the outside means we're reflecting over the x-axis. I'm not going to write what it looks like in the equations because we have these two different equations, but I always give you that, what I call that skeleton, so you see what it would look like for the square root and the cubic root function. Notice they're pretty much identical other than the square root and the cube root. Over here, we don't have a vertex for the square root function, so we just call this our starting point. So our starting point here is at 0, 0, but if we were to shift it left, right, up, down, we would have a new starting point. And over here, remember, we call this the point of inflection. Again, it's not called a vertex because it doesn't, it's not on one of those extremas, so it's not changing direction, but we call that the point of inflection and the starting point. And so that's what we're going to do here. We're going to list our transformations from the parent function. We're going to write some equations, and then we're going to go ahead and graph. Here we go. So the first thing they want us to do is just list the transformations from the parent function. So this first one, our parent function is the square root. And all it looks like it's been doing is it has been shifted to the left 2 from this positive 2. Even though it's not inside the parentheses, all of it is underneath that radical. Okay, so that's what you're looking for there. And that negative 4 is on the outside, so that means it's went down 4. And that is it. The second one, we have the cubic root. First thing I see is a negative out front, so that means we reflect over the x-axis. I also see a 2 out front, which means it's a vertical stretch. And I see an x minus 3 underneath the radical, so we treat that like it's inside the parentheses, so that means it's going to the right 3 units. And then lastly, we have another square root. Notice underneath the parentheses, we do have a negative 2x. If this radical would have extended all the way over, we would have definitely had to factor out that negative 2. But because that negative 6 is not included, there's no change in factoring out the negative 2 or not. So that negative underneath the radical, aka inside the parentheses, is a reflection over the y. The 2 is a horizontal compression. And the negative 6 on the outside means we're going down 6 units. This should not be any different than what you know from the beginning of the school year. Now for example 2 and 3, we're going to write the equation of a square root function that has been transformed and of a cubic root that has been transformed. So the first one says, write the equation of a square root function that has been vertically stretched by a factor of 3 and reflected over the y-axis, followed by a shift up 6 units. So this means we have a square root function. Vertically stretched by a factor of 3 means I put a 3 out front. Reflected over the y-axis means there's going to be a negative underneath that radical. And then followed by a shift up 6 means I have a plus 6 on the outside. We want to make sure we're not putting that underneath the radical. So even if you want to make that radical maybe just a little bit shorter, you can too. And that's it. Everything was in the correct order. We didn't have to distribute anything. So this is our final answer. In example 3, we're taking a cubic root function that has already been transformed, and it's already been shifted to the right 3 and up 2, and we're going to do some other things to it. We're going to shift it up 3, left 2, followed by a reflection over the x-axis. So let's do these shifts first. So if I have already gone right 3 units and then I want to go left 2, then that means I've really only gone right 1 unit, because -3 plus 2 is -1. I've already gone up 2 units and I want to go up 3 more. So that means I'm up a total of 5 units. Now I'm going to follow by a reflection over the x-axis, which means this entire function is now going to get flipped over the x-axis, which means if I was already up 5 units, but then I flip over the y-axis, I'm really now down 5 units. And there's our final answer. And now we can get into graphing. We're going to list out the transformations and we're going to graph them. So we want to list the transformations, find that starting point or that point of inflection, and then sketch the graph and find the domain and range. Notice A, C, and D are all your square roots, and B, D, and F are all the cubic roots. So maybe we want to do everything on the left first and then everything on the right so that we're in that same frame of mind, or maybe you want to practice going back and forth from square root to cubic root. It's up to you. I'm going to go ahead and start with A, obviously. And I see that for A, I have a vertical stretch, shifting right 1 and up 3. So that means my starting point is here. Normally for a square root, we would have gone right 1 up 1, right 4 up 2, right 9 up 3. But because it's been vertically stretched, my ups are going to get multiplied by 2. So instead of going right 1 up 1, I'm going to go right 1 up 2. Instead of going right 4 up 2, I'm going to go right 4 up 4. And then if we can fit the 9, right 9, 5, 6, 7, 8, 9. It was normally 3, now it's going to be 6. And so now we see that square root function. We can clearly see that it's been vertically stretched. Now our domain starts at 1 and it goes to infinity, and that range starts at 3 and goes to infinity. Let's go ahead and switch to the cubic root, excuse me. Negative in front means I'm reflecting over the x-axis. 2 in front, vertical stretch. Plus 3 is on the outside, so that means we're going up 3 units. So my point of inflection is going to be at 0, 3. Normally we would have gone right 1 up 1, right 8 up 2, left 1 down 1, left 8 down 2. Let's write that out. Normally we would have gone right 1 up 1, right 8 up 2, left 1 down 1, left 8 down 2. The reason I'm going to write this out is because we have a reflection and a stretch. Reflecting over the x-axis means what was now up is now going down. What was down is now going up. Vertical stretch means these numbers also get multiplied by 2. And so from that point 0, 3, I'm going to go right 1 down 2 and right 8 down 4. I'm going to go left 1 up 2 and left 8 up 4. And so now I can see that that cubic parent function has been flipped and has been vertically stretched. Domain is still negative infinity to positive infinity. Range is still negative infinity to positive infinity. Really, you should be able to stop the video right now and do some on your own. I'm going to keep going though. Remember in C, we see a negative x plus 2 underneath that radical. Well, we need to factor out that negative, so we really have negative x minus 2. That means we're reflecting over the y-axis and going to the right 2 units. So I'm going to start with that starting point of right 2 units. There's been no stretches or compressions, but just a reflection of the y-axis, so which means I was going right and up. Now I'm going to go left and up. It's still going to be left 1 up 1, left 4 up 2, and left 9 up 3. And there we have it. This time my domain is from negative infinity all the way to that 2, and my range is from 0 to infinity still. So range actually didn't change this time, just domain. I'm going to go ahead and switch to cubic root. Let's go cool. Nothing that I need to factor out. This is a vertical stretch and a shift right 3. So I'm starting here. This is my point of inflection. Instead of going right 1 up 1, right 8 up 2, left 1 down 1, left 8 down 2, I have a vertical stretch of 2. So I multiply those by 2. And so now I'm going to go right 1 up 2 and right 8 up 4. 1, 2, 3, 4, 5, 6, 7, 8. So somewhere about right here. Left 1 down 2, and then left 8 down 4. And then I see that cubic root function that has been vertically stretched and shift to the right 3. Domain, still negative infinity to positive. Range, still negative infinity to positive. E, definitely want to factor something out there. So this is now really negative square root of 1/2, open parentheses, x plus, x that would be x plus 1. And then I still have my plus 3 on the outside. So this means I am reflecting over the x-axis. I am horizontally stretching. I'm going to the left 1 and up 3. So left 1 up 3. Oh, sorry, I was looking at the wrong one. There we go. Left 1 up 3, and then I am flipping over the x-axis, so what was up is now going to go down. So normally we would go right 1 up 1, right 4 up 2, right 9 up 3. So now these are all going to go down, and I also have a horizontal stretch. So this is now going to be 2, 8, and 18. So then instead of going right 1 up 1, I'll go right 2 down 1. I'll go right 8 down 2. 2, 4, 6, 8 down 2. I can't fit right 18, so then this is just my graph. Domain here is going to be from that negative 1 to infinity. Range this time is going to be negative infinity up until that 3. Okay. And our last one, again, we have to factor something out. What color do we want? Pink. All right, so this is really the cubic root of 2 times x minus 2, and then minus 1. So that means we have a horizontal compression, a shift to the right 2, and down 1. So right 2, down 1 is our point of inflection. And there is a horizontal compression. So normally for the cubic root function, we would have gone right 1 up 1, right 8 up 2, left 1 down 1, left 8 down 2. But because of the horizontal compression, we're going to change these numbers and we're going to divide them by 2. So this is now 1/2, 4, 1/2, and 4. So from this point, I would go right 1/2 up 1, right 1/2, up 1 would be somewhere about right there. Left 1/2, down 1. Right 4, up 2. So right 1, 2, 3, 4, up 2. 1, 2, 3, oh, 1, 2, 3, 4, and 2. Okay. And then let's see, the next one would have been 3, that would have been 27, right? But half of that would be, just seeing if we can fit it, would be 13. Nah, we can't fit it, so we'll just leave it as is. And that has been horizontally compressed and shifted. Domain, still negative infinity, positive infinity. Range, still negative infinity, positive infinity. And there you have it. Easy as that, guys. See ya.